In our last video, we introduced the idea of thinking about the derivative as a function. And so here what we're going to do is we're going to try and think of the connection between that derivative function and the function that it came from. So this is derivatives and functions. First, we're going to talk about differentiability and continuity. This is going to be a nice result that we'll use a whole bunch in this course. We'll also talk about where a derivative may not exist. I know we hinted at that last time when we were talking about the definition of our derivative. And then lastly, we'll talk about the connection between graphs of derivatives and graphs of functions. So graphs of f and graphs of f prime. So let's get this started. We'll start off with differentiability and continuity. The big result here is that differentiability implies continuity. Remember, differentiable means that the derivative exists. So if f is differentiable at a point A, again, f prime of A exists, then f must be continuous at A. So if we have that our function is differentiable at a point, we know it has to have been continuous at that point as well. Here's the proof. We're really going to rely on this identity that I'll talk about in a second, but we need to show specifically that the derivative, the derivative exists, if this limit exists, then the limit of our function is equal to the function value, right? That's what it means for continuity. So this identity, notice that if we just kind of go backwards through here, these two pieces can get canceled out, and then we've got a minus f of a plus f of a. So really, this is an identity because these two things are equal to each other, but we just say that as long as x is not equal to a, because see how we're dividing by x minus a here? We got this division by 0 if f was equal to a. So this seems like we're overly complicating what our function is, but the key here is this. Doesn't that look like something? Doesn't that look like a derivative? So let's consider the limit using this identity. We're going to apply a limit of, as x approaches a, to f of x here. But since f of x is all this stuff, we're looking at the limit of all of this stuff as well, right? And so then what we can do is apply the limit to each piece. So this is really the limit of f of x minus f of a over x minus a times the limit of x minus a plus the limit of f of a, again, when x is not equal to a. And for each of these things, we should be able to recognize what's going on. This one here, we should know that's f prime of a. This one should be easy, right? This is an easy limit for us to find. Plug a in for x, and we get a minus a. And this one is a constant because there aren't any x's in here, so it's f of a. So what we get is f prime of a times a minus a plus f of a, or 0 plus f of a, right? A minus a is 0. So 0 times the derivative f prime of a. It doesn't really matter what f prime of a is. That whole first term is 0. So what we've just shown is that the limit as x approaches a of f of x is equal to f of a. So if f prime exists, the function is differentiable at a, then f has to be continuous at a, since we just showed that the limit as x approaches a of f of x is equal to f of a. Bang. All right, differentiability implies continuity. Cool. What does that actually do for us? Well, a couple things to just note. This is sometimes restated in maybe a bit of a more interesting way for us for now. If differentiability implies continuity, then that means that if f is not continuous at a, then that means f can't be differentiable at a either, since if it's differentiable, it has to have been continuous. So if we can see that something is not continuous, then we know that the derivative won't exist there. But be careful, it doesn't mean that if the function is continuous that it is differentiable. There are lots of cases where it's not that's not true. There are cases where you have functions that are continuous for all real x values, but the derivative doesn't exist for any of them. It's kind of crazy, the Weierstrass functions. In a lot of cases, though, we might note that f is continuous and differentiable, even though we could just say it's differentiable, because that covers both. But what we'll also do is we'll talk about a function being continuous on a closed interval and differentiable on an open interval, where really we try and specify that we have one-sided continuity at the ending points, right? So sometimes when we say continuous and differentiable, we're really just making the distinction between this closed interval and open interval. We'll get to all those kinds of things later. All right, so when else could a derivative not exist? Discontinuities are clearly going to be a problem, but what other types of things could be problems? Oh, we just should remember, a derivative is really a limit, right? So let's think about a limit of a function not existing. Well, there's really two possibilities. The limit of a function doesn't exist if the function values don't go to the same thing on the left side and on the right side, right? If those one-sided limits don't match up, then our limit won't exist. And our other case is if the limit is an infinite limit. If the left and or the right side limits go off to infinity or negative infinity, then clearly our limit doesn't exist because those aren't real numbers. Remember, a limit only exists if the function gets arbitrarily close to some single real number L when x gets sufficiently close to a. So if it doesn't approach a real number, like it goes off to infinity, our limit doesn't exist. So if a derivative is a limit, let's think about what that limit really is. The limit is really a slope. So okay, the derivative is really a slope. So the derivative doesn't exist if not necessarily the function values don't approach the same thing on the left and the right, but if the slopes don't approach the same thing on the left and the right. So if we have a different slope on the left versus the right, a really classic example of this is just the absolute value function. The absolute value function looks like this. It is a piecewise function that we could write this way. Oops. What am I writing here? That's equal to negative x if x is less than 0, and x if x is greater than or equal to 0. And you can see pretty clearly that there are different slopes on both of these pieces, right? The slope here is negative 1, and the slope here is positive 1. And right at that point in the middle, we have different slopes on the left and the right. We could also say our derivative doesn't exist if not necessarily the limit is an infinite limit, but what that means now, if our limit is really a slope, we're saying the slope is an infinite slope. So maybe we have some sort of infinite slope happening. What does that really look like? Well, an infinite slope just means that the rise over run is really, really, really big, right? So what if we have something like this, where right in the middle we have like a perfectly vertical tangent line. So vertical tangent lines are going to be issues as well. You can say the slope of a vertical line doesn't exist, right? So if our tangent line is vertical, it doesn't have a slope, and so the derivative doesn't exist there. All right, so the three main types of points of non-differentiability. Discontinuities on a function, right? So we might have something like this, or maybe you have some sort of a vertical asymptote or something like that. Sharp corners, sometimes people will call them cusps too, if they kind of curl up like that, where they look like they've got a vertical line, or just sharp corners like that. And vertical tangent lines. This is our classic cube root function. The vertical tangent lines are sometimes hard to see, so you'll notice in a lot of cases where we care about them and you're trying to identify them, they'll be drawn in. All right, so those are spots where the derivative doesn't exist. But now, how can we connect a derivative function with the function that it came from graphically? A couple things to keep in mind when we're thinking about derivatives and graphs. The derivative f prime of x, it tells us an instantaneous rate of change of f, or really the slope of the tangent line, right? We said it was a function that when you put in an x value, the thing that we read out of it is really an instantaneous rate of change or slope. We also know how to visualize slope, so that's really good. That's going to be really helpful. And so what we need to do is to connect the outputs of the graph of f prime with the slopes on the graph of f. So when we're looking at the graph of f, thinking about the derivative, we're thinking about slopes. When we're looking at the graph of f prime, we're looking at the outputs, the y values of that function, and those are really slopes of our graph of f. Cool. Here's an example. What I want you to do is to pause the video and just stare at this function for a little bit and see if you can find some interesting points with regard to the derivative. If you want, draw some tangent lines on here. See if you can think about slopes. Make a couple of claims, a couple of statements about slopes on this graph at a couple of different points. Go ahead, pause the video, and think about that. Have you paused it yet? Make sure you do. Draw stuff in your notes. All right, let's talk about this. So 3 points jump out to me right away. The first is right here. What's going on at this sharp corner? Well, we just said the derivative does not exist at a sharp corner. So we know that we're going to have some non-existence over here on our graph of f prime of x. We also might notice that if you draw a tangent line here at the x value of 1, that looks to be horizontal. Same thing down here at our x value of 3. If it's a horizontal line, I know that the slope here is really 0. So on my graph of my derivative, I'm going to draw points where f prime of 1 is equal to 0 and f prime of 3 are equal to 0. That's what I'm saying when I'm saying the slopes at those points are equal to 0, right? So that's something that I know is happening. Okay, so that gives me 2 points and I guess a non-point, right? I know that there's not going to be a point when x is equal to 1 on the graph of my derivative. So now what we need to do is start thinking about other things. Let's think about the slope over on this section here. What kind of slope do we have? Maybe let's think about the sign of that slope. Here, I'm going to say the slope is negative. I don't know exactly what the slope is because I don't have a y scale here. So I'll just say, okay, some negative value for my slope. All right. I also will notice that the slope is constant at every point here. This is like a linear piece, right? And so at every point, the slope is the same. So I might have some sort of a horizontal constant negative value over on my derivative. I'm going to leave this open because remember, my slope doesn't actually exist at 0. I can notice that around 0, it changes from negative to, well, what's the slope right here, just past 0? Let's draw a tangent line in there. Looks like that's positive, and it's pretty steep compared to this negative one, right? So maybe I'll start it way up here. And then as we move forward, what happens? It's still positive, but it gets smaller. So maybe I'll just make this slope get smaller until it hits 1, which right here is where it's at 0. And then here we have a negative slope, and it looks like, it's hard to tell, but it looks like it kind of rolls and gets a little bit more negative, and then down here it gets less negative. But it doesn't ever really get that steep. If I'm kind of comparing, maybe it looks pretty similar from this linear piece. So maybe my slope gets negative. Looks like right around 2 is probably the steepest negative spot. So that's going to be my lowest value of my derivative. And then after 3, it starts getting positive again. And see, it gets pretty steep later on. So that means the slope is big. So it looks something like that. So there's our picture of our derivative. And hey, that's pretty good. I was guessing on the y values, right? But looks pretty close. Not perfect, but pretty close. Neat. All right, here's another one. Again, pause the video, and now we're going backwards. So now you're trying to think of the outputs on this graph, right? They're going to match up with slopes on the graph of g that we'll draw in red over here. So see if you can describe some points on G using the outputs right around here. Cool. Go ahead. Hopefully you're doing it. Hopefully. All right, the first thing that I'm going to notice are these 3 points. These are 3 points where G prime is equal to 0. And in our last example, we found those by thinking about horizontal tangent lines. So I'm going to have horizontal tangent lines somewhere between -1 and 0. Looks like just after 1, and then right around 4, I'm going to have some horizontal tangent lines. I'm also going to notice that over here, I'm not thinking about the slope of this curve. I'm thinking about the actual outputs of the function here. They're very negative. That means I'm going to have a really, really, really negative slope until I get to this point where my slope is 0. So maybe I've got some point here where the slope is 0. Tangent line looks like that. And on the left of that, I've got a really negative slope. And then it gets closer to 0, so it smooths off here. And then it turns positive for a little bit. So I'm going to have a positive slope. My function's going to turn around. And then right around, I don't know, here, I've got another horizontal tangent line until, notice, this blue function is negative again, And so that means my slope is going to go negative. Now let's take a look at this little weird cuspy thing. We have a negative slope and it gets more negative, and then right around like 3-ish here, it's going to start getting less negative again. That's like a steepness, right? So we're going to have a negative slope, and it's going to get steeper and steeper until it hits here. Then it's going to get less steep. So it's going to kind of turn back around until we hit this point right around 4. I'll just put it like right here with a horizontal tangent line. And then our function, our derivative, goes back positive. So our function g is going to have a positive slope. Something like that. I don't know. It's kind of hard to tell. Yeah, that looks pretty close. It's not exactly right. What you'll notice is that I have the right general shape, but the y values are hard to tell, right? That's going to be a pretty common theme that we're going to notice. All right, so a couple of things that we can summarize. We're going to get pretty good at finding the points where the derivative is equal to 0, those horizontal tangent lines. We're also going to know that just knowing that f prime doesn't exist at a point is sometimes not really enough to visualize exactly what's going on, whether that's on the derivative or on the function. That's going to be sometimes a little bit tricky. We'll know a couple of ideas of what it could look like, but we have to get some more detail to narrow it down. And sometimes it's easy to tell the difference between positive and negative slopes on their graph. And so after that, we'll use our ideas of steepness to try and connect all those things. And the main point here is that it's hard to be really accurate. If we don't have a scale where we can actually measure what slopes are, then we can't get outputs on our derivative function. And you'll notice that going backwards is really tough because nothing on this blue graph of my derivative tells us at all about the y values on our g function. So that's tricky too. So that's what we're looking for. Those are some connections that we can make between derivatives and functions, whether we're talking about differentiability and continuity, whether we're talking about graphs of these things, or whether we're talking about spots where the derivative doesn't actually exist. That's what we've got. We're going to move forward into starting to actually talk about some real honest-to-goodness derivative rules. You guys have been looking at this limit definition for a little bit. We're going to start moving past the limit definition into some shortcuts that we can do for specific function types. So that's what's coming up.